All right, Algebra 2, we're starting Chapter 7. So we're going to start looking at higher degree polynomials and roots and such. Okay, so 7.1 is nth roots and rational exponents. You kind of have some sort of idea on this, right? We know a square root. Okay, so if I ask you about the square root of 4, right, you would be able to tell me that that's technically plus or minus 2. It's the square root of a number is what number, when multiplied by itself, gives you the original number, right? That's why the square root of 4 is 2 or negative 2. This idea extends to any type of root. So third roots, fourth roots, fifth roots, and continuing like that. So for example, right, a root is still this check mark looking idea, and then it has a number here. So this would be the third root. Okay, so the third root of 8 means what number times itself 3 times gives you 8. Or we could say 2 cubed. So it would be the cube root of 2 to the third, because 2 to the third is 8. So then that's 2. Okay, fourth root, right? That's the number here. So what number times itself 4 times gives you 81? That would be 3. Okay? So in general, you can say that for an integer greater than 1, if b to the n equals a, okay, then b is an nth root of a. Also could be written as the nth root of a is b. And n is called the index on the radical, okay? So if we keep looking at this idea, okay, let's look at square roots, right? So the square root of a times the square root of a is a, right? The square root of 2 times the square root of 2 is 2. So if I let k equal the square root of a, then that's a to the k times a to the k equals a. Properties of exponents tells us that a to the 2k then equals a, but they have the same base, so their exponents must be equal. So k is 1/2. Meaning then that the square root of a equals a to the 1/2, right? Because here I said k is the square root of a. So I solve for k. Or I'm going to substitute a to the k, sorry, for the square root of a, not just k. Okay, so it tells us that the square root is a to the 1/2. Similarly, if I do the cube root of a times the cube root of a times the cube root of a, we would get a to the 1. I can solve, right? Cube root of a times cube root of a times cube root of a gives a by the definition. Same idea here, and then I say a to the k times a to the k times a to the k. So a to the 3k is a. So k is 1/3, right? So then that tells us that the square root of a is a to the 1/2. Cube root of a is a to the 1/3. I could do the same thing and get the fourth root of a would be a to the 1/4. Okay. Continuing this pattern, in general, we can generalize it and say the nth power or the nth root of a can be written as a to the 1/n for any n greater than 1. Okay? Then, if we have n being odd, then a has one real nth root. Right, so nth root of a is a to the 1 over n when n is odd. If n is even and a is positive, then there's two real roots. That's like the square root, right? So the nth root of a then is going to be a positive or a negative a to the 1 over n. If n is even and a is 0, okay, then there's one real root. That would be the nth root of 0, which would be 0 to the 1 over n, which is 0. And if n is even, but a is negative, okay, there are no real roots. You can take an odd root of any number. With an even root, it depends on the value of a. If a is positive, you'll get 2. If a is 0, you get 1. And if a is negative, you get no real roots. Okay? So kind of see what that means. So I want the fifth root of negative 32. Right? N is odd. So that means there's one real root. So we're looking at the fifth root of negative 32. Okay? Well, negative 32 would be negative 2 times negative 2 times negative 2 times negative 2. So that's 16 times negative 2, which is negative 32. So negative 32 can be written as negative 2 to the fifth. So the nth root of that would be negative 2. Okay? Whereas if I said the second root of negative 16, right? We're saying that's the square root of negative 16. It's not real because n is odd, okay? Or n is even, sorry. Looking at the third root of 64. Okay? I could say that's 64 to the 1/3. 64 can just be written as 4 to the third power. So that would be 4. Okay? Rational exponents don't have to just be in the form of 1 over n. You could have an exponent like 3 over 2, okay? Or negative 1/2. These are rational numbers. So, if a to the 1 over n is an nth root of a, and m is a positive integer, then we can say a to the m over n is either a to the 1 over n to the m, okay, just properties of exponents, and then that's an nth root, so we're going to say that's the nth root of a, and then I'm going to raise that to the m power, okay, or you could have said a to the m to the 1 over n, which would be the nth root of a to the m. And if that's negative, then just recall properties of negative exponents. That would be 1 over a to the m over n. And then these same properties apply. So it would be 1 over a to the 1 over n to the m, which would be the nth root of a to the m, or the nth root of a to the m. So, right, this is a lot of letters, a lot of understanding. So translating this into numbers, okay? If I have 16 to the 5 over 2 power, okay? What does that fractional exponent mean, right? Well, that means that it's going to be 16 to the 1/2, because I can take the square root to the 5th. Well, 16 to the 1/2 is the square root of 16. Then I'm going to raise it to the 5th power. The square root of 16 is 4. And 4 to the 5th power is 1024. Okay. If I have 64 to the negative 2/3, the first thing I would deal with is the negative exponent, right? So I'm going to make that 1 over 64 to the positive 2/3. Looking at the denominator, that's the root. So can you take the 3rd root of 64? Okay, which you can. So I'm going to write that as 1 over the 3rd root of 64 squared. So the numerator is the index, rephrase that. Denominator is the index, the numerator is the power. Okay? All right. Then the cube root of 64 is 4. And 4 squared is 16. So we get 1 over 16. This all becomes useful when you're solving an equation, right? If I said x squared equals 16 and asked you to solve, you would say, well, I'm going to take the square root of both sides, and I get that x could be plus or minus 4. Same thing happens when it's higher roots now. So if I said 6x to the 4th was 3,750, could we solve for x? And now we can. So we're going to isolate the power. So I'm going to divide both sides by 6 first. And I get x to the 4th equals 625. Okay? Then to the power of 4, so I need to take the 4th root of both sides. It's an even power. The number I'm taking the root of is positive, so there are going to be 2 real roots. Okay? That tells us x is going to be plus or minus the 4th root of 625, which is 5. So we get x equals plus or minus 5. What number times itself 4 times is going to give you 625? Okay, that's how I got 5. All right. And then something like x plus 1 to the 3rd. I already have it factored, right? So I'm going to get x by itself. Instead of multiplying this out, right, you're going to take the power. So I'm going to take that root. So I want to take the 3rd root of both sides. Okay? It is an odd root, so there's 1 real solution. Okay? So the 3rd root of x plus 1 cubed is just x plus 1. Then the 3rd root of 18, that's going to be a decimal, so I can just write that as the 3rd root of 18. Because it's an odd root, I don't do the plus or minus. And then get x by itself, subtract 1 from both sides. So you can write that as x equals negative 1 plus the 3rd root of 18, or the 3rd root of 18 minus 1. They mean the same thing, okay? So you can simplify these if they're perfect roots or factors are perfect roots. But for this, that's it, okay? So this is just being able to write rational exponents using powers. And solving from there. Okay, so that is 7.1.